Good day, everyone. Moving on into electrophilic addition part 2. As stated before, we're looking to form three-membered rings, either being existing as intermediates or existing as final products with concerted electron pushes. So there are going to be a total of 8 different types of reactions to discuss today. First being a cyclopentane ring formation, i.e. Carbene chemistry. So carbene chemistry involves some kind of carbene so this is going to be C or carbon attached to two types of branching substituents, and then it's going to be doubly bound to an N2 group that's going to isomerize or kind of push some electrons around and basically get photolized with UV light. Okay, so in this case is a little bit more extreme. You're going to have this cis alkene here that's going to have a electrophilic addition with a carbene, which is going to be an sp2 hybridized species, missing two, a carbon that's essentially missing two single bonds or one double bond to it. So in other words, it's going to be establishing these two bonds that you see right here that are about the plane of the page. Second that you'll see are so actually intermediates, so it's going to be a dihalide from an alkene. So this is an alkene species. You probably can't make it out too well there, but essentially you're going to form brominium or chloranium cation, and as a result, this is going to be highly electrophilic. Either carbon is going to be highly electrophilic, and you will have some nucleophile that will come in and pop this ring open, and you'll have a mixture of different products. Now, when we're referring to a dihalide species, well, it's not really going to form a dihalide, but you can use some kind of halide gas, and then in the presence of water, you're actually going to do the same type of three-membered ring intermediate that's going to be positively charged. Get that one of those bonds booted off with the slightly nucleophilic water molecule, and then once a proton transfer has occurred, you're going to have an anti-addition about that double bond with OH opposite of where the halide is going to be. And then you're also going to get an enantiomer. So if you can recall back from chapter 10, I believe, if you were to deprotonate this and work it up under heat, this can actually cyclize and boot this good bromo leaving group off. Again, chloro is also going to be a good leaving group, so you'll form an epoxide that way. More straightforward way of forming an epoxide is using MCPBA. So this is meta chloro, so meta with respect to this peroxy benzoic acid. So benzoic acid, like you would see right here, but since you have this sort of peroxide, this is going to be a peroxy acid right here, this moiety here. Okay, so effectively this particular oxygen towards the end is going to be dumped off onto that double bond syn. Okay, and then things are going to cyclize around, and then you're going to get metachlorobenzoic acid as a byproduct. Now what you would see is something like this. as a product. And seeing as it's a meso compound, meaning there's going to be some kind of axis of symmetry about this particular compound, that means that you're going to not really have any type of stereospecificity. So if this were going into the plane of the page or out of the plane of the page, doesn't really matter because it's just tacking above or below that particular pi bond. Okay, so that's the fourth example. Fifth through eighth are all going to be hydration reactions. So it's sort of like what you saw before where it's an acid catalyzed hydration. So if you were to think about it, for this particular reaction, let's say we have hydrogen source, which is H2SO4, proton source, whatever. That alkene is going to pick it up just like you saw in the last chapter. Okay, so that hydrogen is going to go to the the less substituted carbon. So in other words, up here. Okay, and then you're going to have that particular carbocation. Is it the most stable? Nope. So there's going to be that hydride shift, which I'll just write with a tilde and an H there, capital H. And this tertiary carbocation is going to be more resonance stabilized than this one, which is just going to be standalone. Okay, so you're going to have this intermediate. And then, of course, with water, then proton transfer, you're going to get it's not very proportional. Live with it. Okay, so you're going to have an RS mixture of this alcohol that has been formed. Okay. So the hydrogen first got on here onto this carbon, and then this OH got onto here onto this carbon, eventually after hydride shift, etc. Okay, so you're going to have a racemic mixture of products here. For example, number 6, you're going to use oxymercuration reduction. This is what I refer to as the wax on, wax off set of conditions. So in other words, you're tacking on this mercury group onto the double bond so no hydride shift or rearrangement can occur. So you're going to have a positively charged species from that ring formation. And what you're going to do is actually have a hydration, again, RS, right, where you're not going to have any rearrangement. So this is particularly attractive if you're just trying to hydrate one alkene that could otherwise revert to something else. Okay, so your book or your text actually has something that's kind of analogous to it. I think it's just a geminal double bond here without this methyl to make it tri-substituted. Same difference. All right, so hydroboration oxidation. So this is treating a primary alcohol or a secondary alcohol, or forming a primary or secondary alcohol. That is. So BH3 in the presence of THF. THF, if you're unaware, is this. It's a rather common aprotic solvent to be used. So one of those lone pairs can actually coordinate with boron to stabilize and give it a full octet. Remember that boron's going to be in group 3A, so in other words, it can be amended to 3 things and have a zwitterion if you have a complex with that and THF. Okay, now that's why you see this sort of line here between BH3 and THF. BH3 is going to amend to that double bond, and for reasons I'll show you later, there's this particular polarity to that BH bond itself. So the second half is going to be oxidation, where you're going to use peroxide species, NaOH, and then water. And you're going to get a syn addition product. Okay, so notice here how it is not Markovnikov, it is actually anti-Markovnikov. Okay. Last one we're going to talk about is dialkyl borane, mitigated hydroboration oxidation. So in other words, it only has one equivalent of BH here. So with this particular mechanism, you're going to see 3 BOC, not for blue oyster cult, but for 3 BOC substituents surrounding that boron. So in other words, it's sort of a do-si-do, and that particular, those 3 ligands that are hanging off of boron are actually going to be oxidized with some of the oxygens that you see here in the second half of the reaction. Same thing goes here, except again, you're only going to have one. So in other words, you're going to form an anti-Markovnikov product here, but instead of transforming this to a ketone, again, if it's going to be anti-Markovnikov, you're going to form, let's see, 1, 2, 3. So 1, 2, 3. So you're going to have an aldehyde as a terminal species here. Okay. So that's the transformation. Again, mitigated, meaning that you're only going to have, this is actually going to put hydroxyls on the alkyne not once but twice. So in other words, this is kind of controlling with these kind of bulky substituents, these alkyl substituents that you see on both sides attached to boron. Okay, so starting with carbenes. So again, you're going to use high energy light, presumably UV, to break up this bond here. So you're going to form N2 gas irreversibly. It's going to go up into abundance with the rest of the atmosphere. And then you're just going to be left with an sp2 hybridized carbon here, right? So you have 2 things that can be singly bound to carbon here. And then this lone pair is going to attack in concert with the alkene. In this case, it's going to be a cis alkene. And then the pi bond is actually going to reach back out to the carbon. And then you're going to form a cyclic 3-membered ring that's going to be slightly strained, right? So you can think of, the model kits from back the beginning of the semester, where you can see that 3-membered ring kind of really sort of stretching away. Okay. Now, and have a 60-degree bond as opposed to, something a little bit more comfortable like a 110, 120-degree bond. Okay, another way you can generate a carbene is by deprotonating a chloroform or something isoelectronic to this. So once you've deprotonated and you have a negative charge here, notice how this isn't charged. Okay, so you can just do a formal charge calculation and you'll see that it's going to be net 0. All right, so this chloro group leaves, then you're going to have the same sort of carbene, except instead of having hydrogens attached to it, once again, sp2 hybridized, it's going to have the same sort of concerted reaction mechanism here. But notice how instead of having things cis, things are going to be trans. So in other words, if you were to have everything about the same plane to make that sort of triangle, let's say that the chloro group is going to go in, another is going to stick out. And then you're going to have, say, something sticking out here. So CH3 group. Another CH3 group sticking into the plane of the page. Okay. So it's not going to be stereo specific. Okay. So that's the first example with carbines. Pretty straightforward chemistry. So what's really cool about these concerted reactions is there's just really not a whole lot of arrow pushing to pay attention to. It all kind of works in concert here. So now we have, looks like 3-methyl cyclohexene. So this pi bond is going to coordinate to this bromo group. One of these these lone pair electrons is going to coordinate back. So you're going to form this brominium ion, cation, that's going to be highly ring strained because bromo group is so big. And it's electronegative, so it's going to really pull these electrons further apart from carbon, making them more electrophilic. So therefore, if a bromo group comes in or comes out, whatever, from the plane of the page or out of the plane of the page, what have you, it's going to boot this bond off, or if it were to come in from the opposite end, it will rip this bond off. And so you would have an anti-addition no matter what. Okay, so you're never going to get a syn addition with this dihalide formation. Almost drew chlorine there. Okay, so this is a product you would expect amening to the alkene. All right, number 3, adding water to the mix. So it's a better nucleophile than Br minus a Cl, like what we have in this particular second part of the synthesis. Okay, so to pop that ring open now, we have water, again, which is going to act as a weak nuke. Why am I hitting it at this particular end? Well, there's a few more carbons here that's going to kind of lend electron density in over there via the inductive effect. Okay, so in other words, we're going to see this positive charge now. This is going to come off to go back to bromine to satisfy its charge. Okay. I'll say that's sticking out. It's going in. Okay, so we have another water hanging around, surely. It is going to pick up that hydrogen and stabilize and neutralize the charge. Bromo group. And then OH on the opposite side. Again, going into the plane of the page. So you would have an enantiomer of this too. All right, now the MCPBA or epoxide formation is simply a matter of a lot of electrons getting pushed around. So you see a 4 in total in concert moving about. So this pi bond is going to flip over and pluck off this hydrogen. Meanwhile, the hydrogen-oxygen bond is going to fall over to where the alkene is. The alkene is going to push its pi bonds back over to the oxygen. And these electrons connecting these two oxygens together are going to flip over and claim the octet about that oxygen there and the carbon here. All right, so again, it's going to be syn addition, right? So it's going to push these two groups out. Just that's how it's drawn that way. And again, this is going to be a meso compound, seeing as it has an axis of symmetry, but it does have some stereo centers there, so, or chiral centers, whatever you want to call them. All right, so last moving on into hydration reactions, you could actually use this as an intermediate and then strike it with H plus or OH minus and get some kind of hydration, or sorry, rather lithium aluminum hydride, treating it with that and then hitting it with some kind of acid to get, you know, effectively the same kind of hydration. Okay, but it's not going to be. I mean, it's going to take more steps, and it's definitely going to be a lot more costly than just going with an acid catalyzed form. Okay, hydration reactions. So as shown before, I'm just redoing this transfer or again. So using H2SO4 to catalyze everything to push things forward. You're going to be adding water. Again, original hydrogen's over there, and the hydroxyl group ended up beta from it. Now, the more controlled, lacking hydride shift mechanism is going to be employing mercuric acetate. So these are acetate ligands that you see here that are attached to mercury. No, the thing not to forget here is that mercury actually has a pair of electrons that can coordinate sort of in concert with the pi bond that's going to flip out and coordinate back. Okay, so you see a positive charge right here. And that's really going to elongate this particular bond because you just have so much that's already feeding electron density into there to stabilize the charge. Okay, so water comes in, breaks off that one bond. Octet remains there about the carbon. And then you have a protic hydrogen right here that water strips off, an additional water equivalent strips off. Okay, so then you have that alcohol that is going to be RS. Remember, if you have any type of cation that's an intermediate, remember this is going to be in sort of a flat plane. So you have to imagine that a nuke is going to come into the plane of the page or out of the plane of the page, just like you saw with our last lecture there. Okay, so anything that's going to have SN1 mechanisms, same kind of business, right? Unless there is no stereospecificity. So if two or more substituents about that carbon are the same, then you're not going to see any stereospecificity. Okay, now one last thing. So racemic mixture here. Again, you don't see any rearrangement from the starting material where that alkene is. Okay, so in other words, H, OH, all about that pre-existing double bond there. Okay, so we'll go over hydroboration oxidation without boring you to death. Oh yeah, another way to keep the mixture or the wax on, wax off experiment or set of conditions, like I said before. So wax on, wax off, I think of the Karate Kid and Mr. Miyagi. So, you know, just applying wax onto something, taking it off, right? So it seems like you're just doing something like Sisyphus, like rolling, rolling a boulder up a hill to just have it rolled right back down on the other side of the hill or out off the mountain, right? It seems like it doesn't make a lot of sense, but there actually is a purpose to this, right? So just like Mr. Miyagi, you're not going to question him or it's going to snap your neck like a twig. All right. Hydroboration oxidation. So notice here I have some seemingly arbitrary values. Those actually are electronegative values. So you have 2.06 here and 2.20 here. So that means that hydrogen is going to be slightly electronegative relative to boron, meaning it's going to pull some electron density away from boron. So in other words, this is sort of like a Lewis acid, if you will, superacid. Not to the same extent you would think of, like, say, aluminum and chlorine, or aluminum trichloride or something like that. But what it is going to do is actually amend to this double bond that you see right here. So this is taken from one of the examples in your text. I believe is in 12.52b. Okay, so BH3 is going to amend to this double bond. All right, so you can imagine this B and this H here. And the boron group is actually going to go to the less kind of electron-starved species. So in other words, over here, because on this side, if you were to place where that hydrogen is over here, this, so you have what, 1, 2, 3 carbons all feeding in electron density over here. So a positive charge would more likely end up over here as an intermediate, right? So not so much here. So there is some kind of selectivity. Now, what that means is you're going to get syn addition, anti-Markovnikov. So your two products are going to look like this. And if you ever question this, you can take a look at the mechanisms in your text. Okay, so without going into too gory of an explanation here and not bore you to death, notice how both the hydrogen and the OH, again, this is going to be a hydration reaction, are both going to be about the same side of that ring, okay? Again, because that B and H bond pre-exists here. The oxidation step, i.e. the second half of the experiment, is what puts that OH there and replaces that boro group. Okay, so in other words, this bond kind of breaks apart and that hydrogen sticks there. Okay, so the other, I better draw that other fused ring, doit. Okay, and that H and OH are again going to go into the plane of the page, so you're going to have effectively an enantiomers of one another. So they're going to be they're going to be mirror images if you were to flip this over. Sorry, this is supposed to be a cyclohexane ring that's fused on. It may not look that way. Try not to butt heads here with the plus sign that was here before it. It's not going away. Okay, so you're going to form enantiomers, like I said. Okay, so on to the eighth the eighth and last reaction, not the eighth wonder of the world. We're going to have that BH single bond yet again. Again, notice hydrogen is going to be slightly more electronegative. So you're just going to have that single BH bond amended to this this alkyne, right? So really what you're going to have for an intermediate here is you're going to have H and then BH and then B, not BH, but B whatever, this isoamyl, whatever. I'm just going to write B, R, 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 R. Good enough? Good enough for me. Okay, so now we have that methyl group that's terminal on the right, closest to where the boron group is. And then we have this pH, again, kind of cis to where everything is. This is going to be syn addition. These oxidative species are going to basically supplant what is, here is this boron, this substituted boro group. So it's going to be different in terms of mechanism to what you see right here. Again, you can take a look at chapter 12 and that particular mechanism. It's very much involved. I'm not going to ask you anything involving it. You know, that's there for your reference. I'm just trying to really drive home here that you're going to form an anti-Markovnikov product. In this case, you're going to form, not so surprisingly, an enol. Again, syn addition here. And what you know about enol versus keto forms is that very little of it favors that form. Very much of the keto form is more stable. Okay. So in other words, this is going to be the final product that you get from that particular reaction. So the O winds up over here. So again, that's anti-Markovnikov because this is going to be more positively charged from this electron withdrawing phenyl ring. Okay, so let's apply this to synthesis and wrap things up. So for the first step here, since this is terminal as opposed to, you know, disubstituted, what you see here, this alkyne is actually going to get transformed into, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. All right, so going further from, so this is D from 12.52, that one transformation I just did. Now, BR2 and acetic acid, if you can't kind of dig it out of your skull from chapter 10, that's going to be an alpha bromination. Remember, it's going to just stop at 1 because it's acid catalyzed. Base catalyzed is just going to brominate further. So you're going to get alpha bromination just once about that alpha carbon. So this is almost analogous to what you would see if you had, let's say, a quaternary carbon on the opposite side of that carbonyl. Treat this with NaOH and heat, and you're going to get an elimination product. So in other words, you're going to have a conjugated aldehyde, sorry. Okay, so if you were to treat this aldehyde with NABH4 and ethanol, remember that NABH4 in this particular instance is going to be a mild reducing agent. So it's going to reduce this aldehyde into an alcohol. And this is not an enol. Remember, there's an extra carbon here, so there's no sp2 sort of construct here. There is one right here where this alkene is, but this is sp3. Okay, so now you're going to use this NaH, which is sodium hydride. Is it a nucleophile? Nah, but it can make one. Okay, so now that we have our nuke, which is irreversible, it's going to now perform an SN2 with that chloro group. And then you're going to form this ether. Voila, it's all done. That's all you need to know for electrophilic addition. And if you have any questions, again, feel free to hit me up during office hours. And if not, we'll just kind of go over this quickly on the review and get you geared up for exam 3. All right, everybody have a good one. Take it easy.